In this video we're going to examine a concept known as static stability. We're going to do so for dry parcels of air. And so what we're doing is asking, if I give a parcel of air a small vertical displacement, what will its stability be afterwards? So consider a parcel of air at a height z0, and after a small perturbation dz, its height z is equal to z0 plus dz. The parcel will ascend at a dry adiabatic lapse rate, and so it will move from a virtual temperature Tv0 dashed to a virtual temperature of Tv dashed at height z. Likewise, the environmental lapse rate in virtual temperature, the parcel will change temperature from Tv0 to Tv at z. So we can write out expressions then for the temperature of the parcel of air and its environment at its new height z. Tv is Tv0 minus gamma v, z minus z0, which is our small perturbation dz. And remember that gamma is minus dt dz. And likewise for the parcel, Tv dashed is Tv0 dashed minus gamma v dashed multiplied by z by minus z0. And then we insert the terms for Tv dashed and Tv into the buoyancy equation. dw dash dt is equal to g on Tv, Tv dashed minus Tv. And when you do that, you end up with the equation as shown. So let's simplify that equation. Firstly, we'll let z0 equal 0. And secondly, the parcel of air starts in thermal equilibrium with its environment. So its virtual temperature before the perturbation is equal to that of the environment. And so we end up with a new buoyancy equation. dw dash dt is equal to gz on Tv multiplied by gamma v minus gamma v dashed, which is the lapse rate of virtual temperature of the parcel of air. So that's our equation rewritten. If gamma v minus gamma v dashed is less than 0 and z is a positive displacement, then dw dash dt is less than 0. In other words, there's a negative acceleration and the parcel is stable. So we can write our stability criteria then in terms of the lapse rates of the virtual temperature. If the environmental lapse rate of virtual temperature is greater than that of the parcel, we have unstable equilibrium. If it's less than that of the parcel, we have stable equilibrium. And if it's the same as the parcel, then we have neutral equilibrium. But we can assume two things. Generally speaking, the lapse rate of temperature is about the same as the lapse rate of virtual temperature, and the lapse rate of the parcel is the dry adiabatic lapse rate. And so we can rewrite our stability criteria, as shown in the blue box, that if the lapse rate of the environment is greater than that of the parcel, we have unstable equilibrium. So in other words, if we lift the parcel a little bit, it cools more slowly than its environment, it's warmer, and it has a positive buoyancy. In other words, it accelerates upwards. If the lapse rate of the environment is less than that of the dry adiabatic lapse rate, then we have stable equilibrium, which means that the parcel cools more rapidly along the dry adiabatic lapse rate than that of the environment, which means after a small perturbation the parcel is cooler than the environment and has a negative buoyancy back down to its original level. Finally, if they have the same lapse rates, then the parcel will always be at the same temperature as its environment for that layer, and so we have neutral equilibrium. So can we easily interpret this graphically? Well, yes we can, but we need to go through a little bit of maths in order to do that. Stop the video any time you need to and show for yourself that the equations on the screen follow. Firstly, take Poisson's equation for potential temperature and take the log of both sides, and it gives you equation 2. Then differentiate with respect to z, and the term involving only constants disappears. So we have 1 on theta d theta dz is 1 on t d t dz minus rd on cpd by p dp dz. And we can replace p on rd using the equation of state, or the ideal gas equation, and we can replace dp dz using the hydrostatic equation. dp dz is minus rho g. And so after that we end up with equation 4, that t on theta d theta dz is equal to dt dz plus g on cpd. Now g on cpd is the dry adiabatic lapse rate, and we define the lapse rate of the environment as gamma is minus dt dz, so that we can rewrite our equation now as T on theta d theta dz is equal to gamma d minus gamma. And so we can look at how the potential temperature changes with height and infer whether or not a layer of atmosphere is statically stable or unstable or neutrally stable. So if d theta dz is less than 0, then the environment is unstable. It means that the environment cools more rapidly than the parcel of air. If d theta dz is greater than 0, then the environment is stable. The parcel of air cools more rapidly than the environment. And if d theta dz is 0, then the environment and the parcel of air cool at the same rate, and so we have neutral stability. So we can compare the environmental lapse rate to the dry adiabatic lapse rate and assess the stability of air, and that's done graphically here. Here's a visual summary for unsaturated motion. What's indicated, firstly, these dashed lines are dry adiabatic lapse rates for 3 layers. Now let's put in a temperature profile. You can see that the lapse rate of the environment is greater than that of a dry adiabatic layer. And so for this particular layer, theta decreases with height. So it's unstable. For the second layer, the lapse rate is lower than that for a dry adiabatic lapse rate. So the parcel of air ascending at the dry adiabatic lapse rate is always going to be cooler than the environment. And so theta is increasing with height, and therefore it's stable. And finally, our third layer, the lapse rate of the environment and the parcel are the same, which is a dry adiabatic lapse rate, so potential temperature is not changing with height, and so we have neutral stability.